Thank you very much for having me, and thanks to everyone who's tuned in today. Yeah, so I'm going to talk about building a piano, sort of, in JavaScript. But a bit about myself first. So my name is Sophie. I'm a senior web engineer at Monzo Bank in the UK, and I also lead the web discipline for the product side of the organization. And I'm also a keen musician, so I have a choir that I conduct songs for and arrange pop songs for, and I do make some music myself as well. And I've got a website where I blog about tech stuff, which is localghost.dev. But you can find me on Twitter as well if you prefer tech-related shit posting. So this is what I'm going to talk to you about today. This is my virtual piano. You can click the keys and it will play notes, or you can choose kind of scales and chords for it to play. And I'm going to talk you through the musical theory behind it. I'm going to talk to you about how it works, and I'm going to show you a bit of the web audio API that powers it. So some background about how this came to be. My choir has a retreat every year. So we go away for a weekend and we sing, we have workshops, we drink wine and we cry, and it's amazing. And obviously this year we couldn't get together in person due to the pandemic. So we decided to have a virtual retreat over Zoom. And I decided it was a great idea to give a workshop on musical theory, because it's something I just kind of absorbed over many years of playing various instruments, and a lot of people in the choir don't have a musical background. So usually with a workshop like this, I'd give the attendees some exercises to do to put into practice what they learned. So if we're learning about different chords, I would split the attendees into groups and maybe try and get them to each sing a different note of a chord to see how it all sounds together. And unfortunately, that doesn't work over Zoom. I don't know if you've ever tried singing with other people on Zoom, but the latency makes it basically impossible. So my mind went to other ways that I could potentially get people to try out chords and scales. And what if we had like a web app that could do that? And yeah, at this point, I realized there was probably already a web app that did that, but I also saw a big opportunity to not do the workshop work and instead build something silly in JavaScript. Because music is one of two great passions in my life, and the other one is procrastination. So it seems appropriate to start off with a bit of musical theory and the science behind it all, because the theory that I was teaching in the workshop actually went into the app itself, which I think is really cool. And I know not all of you listening are going to be familiar with the terminology, so I'm going to cover some relevant terms as well. So sound is made up of vibrations that travel as waves. So the number of vibrations in a particular time period gives us what we call the frequency of the sound. And frequency is measured in a unit called hertz, which is 1 cycle per second. And with the keys on a real piano, you've got hammers inside that actually hit strings inside the piano, and those strings will vibrate at a particular frequency to make the right tones. And Western music uses a set of tones with specific frequencies. And in music, we refer to the individual sounds as notes, particularly in written music. And specifically, we use 12 notes. Each has a letter, A to G. And I'm coming from the British English version of things, so I appreciate that people watching may have a different numbering or lettering system. But yeah, A to G is only 7 letters, and we've got 12 notes. Well, in between those 7 letters, there are 5 what we call accidentals, and they're notes that sound very similar to the ones either side, so they don't get their own letter. And instead, we give them a symbol, and we'll call them sharp or flat, depending on which way we're looking. So an accidental is sharp in comparison to the note below it, and flat in comparison to the one above it. So each accidental has 2 names. C sharp is also D flat. And the division of these notes is based on the frequency of each note. And if you want to know more, the Wikipedia page on musical note is a great rabbit hole to fall down and learn more about that. And yeah, as I mentioned, like not all countries have the same letters. I know, for example, in Germany, what we call B flat is known as B, and what we know as B is known as H or Ha. And the composer Bach used to play a little note pattern in a lot of his songs that went B flat, A, C, B, which in Germany is B, A, C, H, which is basically giving himself a shout out in his own songs, which I love. And the distance between any note and its nearest neighbor, so in this picture, for example, C and C sharp or B and C, is known as a semitone or a half tone. And two semitones will make a whole tone. So generally, when we're talking about musical notes, we're referring to them as they're laid out on a piano, starting from C. And the letters of the notes repeat for all of the notes on the piano in groups, and they go from lowest on the left to highest on the right. And the piano has white and black notes, and those black notes are those accidentals that we talked about. And if the black note, oh, I've done that already, it's to the right, it's a refresher that if it's to the right, it's a sharp, if it's to the left, it's a flat. So the distance between one note and the next occurrence, so for example, from one C to the next C, is an octave. And on a regular piano with 88 keys, there are 7 1/4 octaves, and those octaves are pitched higher and lower relative to each other. So we've got two notes here, both A, in octaves 4 and 5. Ooh, let's see if I'm actually sharing my audio. Always do this. Oh no. I'm definitely a Google Meet user. Apologies, everyone. Video settings. I forgot I need to share my audio. Okay, there we go. Share sound, fabulous. Okay, so so that is two notes, both A, but in octaves 4 and 5. And it's a weird quirk of our brains that we can hear two notes of the same letter in different octaves and kind of just tell they're the same note, but one is higher and one is lower. And so each octave jump doubles the frequency of the note. So that first A is A4, as it's in the 4th octave. And that has a frequency of 440 hertz, which will become important. And A5, that second note, has a frequency of 880 hertz. So scales. Music tends to use only some notes, not all of them. So so each note on a piano has a set of 8 notes that you can play after it to reach the next octave. The word scale used to mean ladder in English, and it is kind of like a ladder to the next octave. So music tends to use the notes from a particular scale throughout a piece or a song, and this is what we mean by a key. So this picture shows 2 octaves of the C major scale written in musical notation. The important thing to know about scales that will be relevant to this talk is that they follow particular patterns, and you can apply a particular pattern to any note, and you can get the associated scale starting from that note. Of course, we love patterns in programming, don't we? So in this example, which is the G major scale, you can see the pattern that creates the major scale. So if we remember that one semitone or halftone is the distance between one note and its right-hand neighbor, and a tone is 2 semitones, then we have tone, tone, semitone, tone, 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 semitone. And that pattern will give us every single major scale, regardless of what note we start from. Okay, code now, please. This isn't music camp. Let's talk about the Web Audio API. It's amazing. It's a really powerful API. You can do some very cool stuff with it. I haven't done a lot of stuff with it. This is kind of, my explorations have been quite limited to kind of synthesizing audio, but you can also play audio files with it. You can analyze audio that's playing. You can make some really cool Winamp style visualizations of playing audio. You can mix, filter, pan, position, and you can do all sorts with it. It's amazing, and it all runs in the browser. And so we talked about sound waves before and the frequencies of the waves that shape that waveform. And synthesizers generate these waves programmatically to make sound. And that's what we need to do in order to be able to make sounds with JavaScript. So we need to build a little synthesizer. We need an oscillator, which in real life is a circuit that produces an alternating waveform. Then we need to define what that waveform should be. We need to know the frequencies of all the notes on the piano to be able to tell the synthesizer what note to play when we press the virtual piano key. And then we actually need to build those piano keys in some kind of user interface. So to get started, we need to access the API, and we can do that by initializing an audio context. And this interface exists on the window object in the browser, in the Big Four browsers basically. So we only want one of these in the app. We don't want more than one initialized, because then we could end up with lots of sounds playing at once. And so this audio context instance that I've created here will give us lots of functions that let us interact with the API. So we need to create the waveform that our synthesizer is going to output. And the shape of this waveform determines the sound that's produced. So a sine wave will make a very different sound to a square wave. So the audio context object will give us a function called create periodic wave, which takes two arguments, arrays of floats that define the various values of the wave. And for the purposes of this project, I just wanted something that vaguely resembled a piano. And vaguely is the operative term here. So like generally software pianos in things like Logic Pro will use real samples of piano sounds. And that wasn't an option for this little project. So I kind of just Googled for a web audio waveform, and I found this bank of web audio samples from Google Chrome Labs on GitHub. And they have this piano-like wave definition, which I dug out of the repo and saved into my project. And it sounds nothing like a piano, which you'll find out later. So now that we've got our waveform, we need an oscillator to turn that waveform into sound. An oscillator generates a constant tone. So we use the function create oscillator to create the oscillator, amazing. And then we set the wave that we've just created on it, and then we connect the oscillator to the audio context destination. And that, in this case, is our speakers. And then we start the oscillator. If you want a simple sine or square wave, like the ones I just played, for example, you don't need to bother creating a waveform. You can actually just set the type property of the oscillator to sine or square. So at this point, our app is playing a fixed tone. It defaults to a frequency of 440 Hertz, which you may remember is A. And in order to go from the note letter and octave of a note to a frequency, I needed to do some maths, which is my favorite. So I did this by Googling to see what other people had done. We used the note A4 as a constant. So this is A above middle C on the piano. And it's actually standardized as ISO 16. It's a reference pitch that instruments tune to. So generally, if you go and see an orchestra, they'll probably tune to this note. And yeah, that frequency, as I mentioned before, is 440 Hertz, which is a lovely round number. And we can then work out the frequency from the number of semitone steps between A4 and the note we're trying to find. So N in the equation here is the number of semitones that we need to go from A4 to the note. So for example, the note C5 is the next C above A4 on the piano, and that's a difference of 3 semitones. So the intervals that I use to calculate the steps are hard-coded based on a single octave. So if we were kind of mapping between notes in a single octave of 12 notes, how many semitones would there be between each note? You can see A is 0, obviously, because it's already A. And we go right down to C, which is -9, and up to B, which is 2 above A. And this is how I translated that equation to code. It takes some letter and number combination. So for example, C5, which is C in the 5th octave on the piano, and it gives us the frequency. So let's break it down. First, we find the interval corresponding to that note within the octave from that hard-coded list I just showed you. And then we calculate the number of steps from A4 to our note by first working out the difference in octaves between the octave that we're looking for and the 4th octave where A4 lives. And then we multiply it by that original number of semitones and add that original interval that we found. And finally, we can calculate the frequency by running that equation that I showed you before. So it's the value of A4, which is 440, multiplied by 2 to the power of the number of steps over 12, few. And then for convenience, I round it to 1 decimal place. I did actually put together a little web app on CodePen that shows you how this frequency calculation works. So I can share that after the talk as well. So in this example for the note C5, we subtract our base octave 4 from the octave 5, giving us 1. 1 times 12 is 12. And then we add -9, which is the interval from A to C. And this gives us 3, which correctly is the number of steps between A4 and C5. And this feeds into that formula. We do the calculations, and then we get a frequency of 523.3. And with these frequencies, I could generate octaves of notes in the form of arrays. So I use these to supply notes to the virtual piano and generate things like chords and scales. And I iterated over the notes in order, calculated the frequency of each one, and then I appended them to an array. So now that we've got the frequencies, we can build the piano. I built it in React. Vanilla JavaScript probably would have worked just as well, but I ported over a JavaScript library called Piano SVG into React because I didn't really want to build my own from scratch. So each note is assigned a numeric ID corresponding to its position in the array of frequencies that I generated in the previous step. Each key is an SVG path rendered by a separate React component that has its own props. And this way I can pass in whether or not it's currently being played and what happens when you click it. I added an on mouse down handler to each key, which sets the oscillator frequency to the frequency at that position in the array, and then an on mouse up handler to stop it playing when you release the mouse button. The piano SVG code takes care of where the keys go on the actual piano itself, and the piano component renders these 2 rows of keys, one white and one black. I won't go into the details of rendering the actual piano, but you can see the code on GitHub, and the repo is open, so I will share that afterwards as well. So with the piano rendered, I can now pass in functions to trigger on click of each key. So as I said, the piano component takes an array of notes, and each key has an ID which refers to that note that in the array that it represents. And the piano itself sits inside a parent component called player, which controls all of the audio operations and manages what's currently playing. Now, I wanted to be able to press a note and have it sound once, just like an actual piano key, but I also wanted to be able to activate a kind of sustain pedal to make the notes continue sounding after I released the mouse button, so that you could kind of play more than one key at once. And I also wanted it to be keyboard accessible. So the parent player component stores whether or not the pedal is active in its state. And then each key has a ridiculous number of event listeners, which is fun. So the on-click listeners play and stop notes when the pedal is active, and the mouse up and mouse down listeners will play and stop when the pedal is off. So as soon as you release the mouse, the note will stop. And those play and stop functions are defined in the parent player component, passed in as props to the piano. And I actually create a new oscillator for each note that plays, because an oscillator can only play one note at a time. So to play multiple notes at once, we need multiple oscillators. And I keep track of those oscillators in the player state as well, and I can stop and disconnect them when I'm done with them. There is a lot of code that goes into this. So yeah, do have a look at the GitHub repo if you are interested in the kind of details of that. So as well as being able to interact with the piano directly, I wanted to be able to automatically play all of the notes of a particular scale. So do you remember how the scales have those predictable patterns that will tell us what the notes are? Well, we can use those to generate the notes of a scale. So I actually put together this table of intervals for various scales, where each number is the number of the interval of the next note from the previous note. So if we look at the first one, which is the major scale that we talked about before, the pattern is tone, tone, semitone, tone, 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 semitone. And so if you think of all these numbers as semitones, a tone is 2 semitones. We always start at 0, which is the first note of the scale, unless we're starting from the top and going down. So we add 2, 2, 1, 2, 2, 2, 1. And that will give us the major scale starting from a note. So then I generated an octave of notes, and I iterated through the scale pattern, fetching each note based on a cursor, which I called current position, and that keeps track of which note we're on. And we add each interval to the current note to find the next note in the octave array. And when it comes to playing the scale, we want to change the frequency the oscillator is playing at regular intervals as we go through the scale. So I actually set timeouts for each note in the scale, in this case, half a second, multiplying by the timeout by the index of the note in the array so that they're staggered. And when the timeout elapses, the frequency of the oscillator is set to the frequency of that note. And we end up with this really nice sequence of timeouts. And the player has to keep track of these timeouts in state as well. So if the user hits the stop button, I can cancel all of those timeouts and stop the scale playing. Now, I got it all working, but I had a bit of a nightmare. For one thing, sometimes the notes just don't actually stop, despite like having the array of those oscillators in the player state. It just seems to lose track of them sometimes, be unable to disconnect them. And initializing oscillators sometimes doesn't work fast enough. So I would get errors from trying to set the frequency of oscillators that were undefined. I had to wrap the function in a promise to force the app to wait until the oscillator had actually been initialized. Ultimately, I decided if it breaks, people can just refresh the page and live with it. That's not my attitude to writing production code, just to make that very clear. And also the accessibility of it is not perfect. So I never thought I'd be building an app that had on-click attributes added to SVG elements. From an accessibility point of view, like if something needs to have an on-click behavior, it should be a button element. As screen readers identify what button elements do, they can recognize that that is something you can interact with, whereas some screen readers won't recognize that an element is clickable if it's just, let's say, a div with an on-click. And in the HTML spec, button is actually not a valid child of SVG. So I just ran with it. I added the ARIA attribute role equals button to each key. And then I had another problem in that the display order of the keys didn't match the tabbing order. So when you press tab to go through the keys, they'd go all the white keys and all the black keys because they're all rendered separately. And what you really want to do is kind of go up and down, like across the keys in order as you would on a piano. So I fixed this by manually overriding the tab index attribute for each piano key. And the tab index attribute tells you where in the tabbing order an element should go. So each key has that ID from 0 to the number of notes on the piano. So I could use this quite easily to determine where the tabbing order would go. And to make sure that the remaining elements on the page before the keys were still tabbable as usual, I just added a kind of arbitrary offset to each of those tab index values so that they always come last. General rule is never to mess with tab index, but I figured this was a special case. Okay, I'm going to try and show you a little demo. There are a couple of other features I didn't show you in this talk. It plays various chords and shows you what note it's playing. And again, yeah, if you want to see for yourself, it's on GitHub. The actual app itself is on Vercel. So let's have a look. So I'm going to warn you, it kind of sounds horrible. There we go. I mean, you play your nice scale. I can put the pedal on. There we go, had to refresh because it's very broken. But yeah, do have a play with that. And I will be around after this talk to answer any more questions. If you'd like to find out any more about the Web Audio API, there's some fantastic resources around, some even more amazing demos of what's possible with it. So I recommend MDN as like the Bible for any kind of JavaScript things. But CSS Tricks has a great article on the Web Audio API. And there's some cool demos of visualization using playing music as well, which I recommend taking a look at. And yeah, thank you very much. You can find me on Twitter. I'm extremely online. You can find my website there as well. And yeah, I'll be online after the talk to answer any questions. Thank you very much for having me.